Our first speaker is a truly distinguished figure who sits at a fascinating intersection of academia, philanthropy, and cutting-edge deep technology. He is the Emeritus Professor of Nanomaterials at the University of Oxford, where his pioneering research explores everything from quantum technologies to the very thermodynamics of timekeeping itself. His leadership track record is extensive. For nearly a decade, he directed the UK interdisciplinary research collaborations in quantum information processing and subsequently led major grant-making initiatives at the Templeton World Charity Foundation. Today, he is bridging the gap between theory and commercial reality. As the chair and co-founder of Quantrologs, he is spearheading the use of machine learning to tune quantum devices with a precision that exceeds human capabilities. His talk today is titled Fresh Perceptions of Reality. Please join me in welcoming Professor Andrew Briggs with a round of applause. To chair this session, I would like to invite Dr. Partha Sarathi, Associate Professor, School of Minerals, Meteorological and Materials Engineering, IIT Bhubaneswar, to the dais, please.
You'll see the slides better if you do it. This amazing conference. I'm a pilot, and this is a picture that my wife Diana took out of the plane in September when we were flying from Scotland to Ireland. So you get a little glimpse of what I do when I'm not doing science. It comes as a surprise to many people, even some of those trained in statistics, to learn that probability is subjective. And I can give you an easy example of this. Supposing that I have a coin, and it's a fair coin, one side heads, the other side tails. I toss it, I catch it, and I put it on my hand, all right? What is the probability that it's heads? 50%. Now, I have a look, and I see what it is. What now is the probability that it's heads?
1.
How do you know? It might have been tails that I saw. So how do you know the probability is 1?
Because that is complementary.
Exactly. So the probability for me is either 0 or 1, but the probability for someone else is 50% still. So the probability is subjective. And we live in a world where we increasingly are subject to uncertainties and randomness. People are beginning to see it in all sorts of areas. The left-hand book is from Tim Palmer, one of Oxford's most distinguished atmospheric physicists. And on the right is a book from John Kay and Mervyn King, two of Britain's most distinguished economists. And we're beginning to find that there's uncertainty in almost every area of life, in science, in atmospheric physics, in life sciences, in healthcare, quantum science, particle physics, economics, entrepreneurship, politics. We're in this world of uncertainty. And the mathematical tool for coping with uncertainty is probability. But we've just seen that probability is subjective, and this reaches a mathematical rigor in Bayesian probability. Bayesian probability is different from frequentist probability. It's the probability that a certain belief is true. And this is Bayes' formula, familiar to anyone who does conditional probability. And it says, well, it's based on the chain rule of joint probabilities, so you can very easily derive the expression. And it says the probability of A given evidence B is the probability of the evidence B if A is true times the prior probability of A divided by the prior probability of B. So what that means is that if I'm given some new evidence, what I rationally deduce about the probability of B being true depends on my prior belief. I'm sorry, if I'm giving you evidence B, what I rationally believe about the probability of A being true depends on my prior beliefs about A and B. And therefore, as we're presented with evidence about things, we can rationally draw different conclusions from someone else who had different prior beliefs about the same issues. One of the most distinguished philosophers of religion, for which he was awarded the Templeton Prize, was Alvin Plantinga. And here's his summary of his life's work from his Templeton Prize speech. What I've argued in a nutshell is this. There are some pretty good arguments for theism, for the existence of God. Maybe none of these theistic arguments are absolutely conclusive, but some of them are pretty good arguments. More important is that what I've argued is that if belief in God is true, if there really is such a person as God, then belief in God is not irrational. My argument very simply is that if theism is true, then in all likelihood, God would make his presence known to us human beings. And as a Christian, I'm confident that God does make himself known to us, but I recognize that people with different prior beliefs might come to different conclusions. And that's not because either of us is applying faulty logic, certainly not because of weakness in the evidence, but because of the different prior beliefs that we bring. Now, one of the important insights in the theory of information is that information is physical. We had a talk about that yesterday. Everything that is going on in my mind is communicated to you through the physical processes of my mouth and the airwaves and so on and so forth. And that's true of all information. I've got lots physically embodied in my computer here. And the connection between information and the physical world is seen very clearly when we erase a piece of information. So supposing I've got one bit in my computer and I erase that one bit of information, there's a very precise amount of entropy that is necessarily involved in that erasure. And the amount of entropy that's involved is Boltzmann's constant, KB, multiplied by the natural logarithm of 2. And this was first articulated by a very distinguished scientist, Rolf Landauer, and it's become known as the Landauer erasure. And over the past year or more, in my laboratory at Oxford, we've been actually measuring this amount of energy, to turn the entropy into an energy multiplied by the temperature. So what I can show you is some experiments we've actually done to measure this physical basis of the erasure of one bit of information. Here is the experiment. It's a silicon chip. Is that pointer working? Yep. It's a silicon chip. Actually, we're just using the left-hand bit of the chip here. So the bit of information is embodied in this little part of the chip here. It's a tiny volume of material, and we control the electrostatic potentials with electrodes nearby, and we adjust it so that there's either one additional electron in this quantum dot or no additional electrons. And then over here we've got a sensor. It's actually a single electron transistor that can detect whether or not there's an extra electron in this quantum dot. And what we're saying in this memory is that one extra electron we'll call a 1, and no extra electron we'll call a 0. So now we've got one bit of information that we can store. And rather importantly, we make the single electron transistor operate very fast compared with anything that's going on here. And that means that we can instantaneously detect the population of this quantum dot. And here's a little trace of what it looks like, okay? So if we adjust things, we can adjust it so there's an electron coming in. It's coming in by quantum tunneling, and it can leave, again, by quantum tunneling, and we can detect whether or not it's there. And what we're going to do in the experiment is to adjust things so that there's about a 50% probability that there's an electron there, an extra electron, or not. So that's either a 1 or a 0. And then we're going to erase it either to 0 by raising the potential of the dot so the electron comes off, or to erase it to a 1, reset it to a 1, so we do that by lowering the potential so that an electron comes on. And here are some experimental data, and I want you to look at the right-hand side when we allow the experiment to happen quite slowly. So we allow the whole process to take quite a long time. And look at this blue set of data here, and you see that in units of kBt, in other words, the Landau unit, the cost of erasure is about 0.7, which is the logarithm to base e of 2, right? Now, there are two ways in which real memory erasure differs from the ideal experiment that I've just described. One of them is that you can't take forever to do things. You have to do it faster. And so if you do it faster, you find there's an additional cost of erasure. So moving left here is taking a shorter time, therefore moving faster. And you find that it increases. And the other difference is that if you're actually operating real electronic devices, you have to operate them at a finite voltage. It's usually about 0.9 volts in most computers. And as we increase the voltage at which we do the experiment, so also the cost of erasure increases. So what we're doing here is something quite extraordinary. We're actually measuring in an actual experiment the amount of energy that is dissipated as heat when we forget one bit of information. So we've made a connection between the process of forgetting and the entropic cost of erasure. And these quantities are very small. So at room temperature, when your phone erases one bit of information, perhaps you delete a photograph or something, the minimum energy cost is 3 zectojoules, okay, 3 times 10 to the minus 21 joules. These are small quantities that are difficult to measure. They're actually even smaller in this experiment because this one is done at cryogenic temperature. Well, that's a classical experiment with classical information, but of course we live in a quantum world, and we're celebrating this year, 100 years since Werner Heisenberg had his sojourn on Helgoland. Here are some of the figures that contributed to the quantum world. And what happens when we try to erase quantum information? And that experiment's actually been done in Vienna recently. It was published in Nature Physics 2 weeks ago. And this measures now the physical cost of getting some quantum information. And in the quantum experiment, we've got an additional factor. And the additional factor comes from quantum entanglement. So the experiment here was to take a gas of atoms and to cool it so cold that it forms what's called a Bose-Einstein condensate. And I hope anyone here from Calcutta will celebrate the name of Bose, because it's about 100 years since he did his crucial insights that probability is not only subjective, but it also depends on, welcome, come and find a seat, please. It also depends on indistinguishability. So at first, the journals which he sent the paper thought it was not significant. He then sent it to Albert Einstein, who realized that this was tremendously important, and they ended up working together, and this is a Bose-Einstein condensate. So what happens is that in the lab in TUV, they make a Bose-Einstein condensate, they introduce a potential here that separates it into two, and then they let go and let the two come together, and you get matter wave interference. Here's a picture of the matter wave interference. And then they make measurements of the various components of the entropic cost when this experiment is done. And there are two ways of breaking it down, but just to simplify it, you can think that one of the ways that you're decomposing the cost of this is the simple heat dissipation, rather like that previous experiment that I showed to you. And the other one is the loss of the mutual information which is involved in the quantum entanglement. And whichever way you split it up, and I've given you two ways of splitting it up here, in the experiment, the Bose-Einstein condensate is an isolated system, and we arbitrarily, or the people who did the experiment, arbitrarily divide it into two segments. One is the system, and the other bit is the environment. And they're saying how much of what was in the system gets dissipated in the environment. This is a human choice, where to make that divide between the system and the environment. And rather crucially, the measurements that you get, each of these curves here is one of these four thermodynamic quantities. And the axis is the length of the system divided by the whole length. Okay, so it's where I put that division between the system and the environment. And the answer that I get for the thermodynamic quantities that I measure depends on that human choice that I've made. So there's a quantum example. Some of the quantum mechanics was devised in the street where Diana and I live. The picture on the left is number 12 Northmore Road. We live in number 5 Northmore Road. And number 12 Northmore Road is where Erwin Schrödinger lived when he received news that he'd been awarded the Nobel Prize. And shortly after that, he moved to number 24 Northmore Road, which is the house here on the right. And he kept there a cat called Milton. And this is where he devised the concept of Konzenverschränkung. That's what the German word for Schränken means. It's like folding your arms. We translate it as entanglement usually. And he also devised here his famous experiment about the cat in the isolated chamber with a vial of poison and a radioactive trigger. Fortunately, as far as we know, he never did the experiment on Milton's cat, which I'm very glad about. Now, he was doing this thinking a few years after the famous debates between Niels Bohr on the left and Albert Einstein on the right. And they had vigorous debates, particularly in the Solvay conference in 1927, about what does this quantum mean? And in particular, what does it tell us about reality? And they never reached agreement about the truth of the reality of the quantum world. Niels Bohr simply wanted to ask what you can say, was kann man sagen, what can you say about the system? In other words, what is the result of an experiment? And Niels Bohr, that was the reality. Albert Einstein found this profoundly unsatisfactory. He wanted to know, was ist, what is actually the case? And some years ago, I was at a conference hosted by Anton Zeilinger, who subsequently won or shared the 2022 Nobel Prize, and we had a little poll amongst us about our opinions about different interpretations of quantum mechanics. And I'll show you some of the results from that poll. You don't need to study them all, except to recognize that about these very fundamental questions, amongst those of us who were gathered at this conference, there's still no agreement. There's still disagreement about whether Einstein's view was right or Niels Bohr's view was right, whether physical objects have their properties well defined, what is the message of the observed violations of Bell's inequalities. This summer, Nature polled about 15,000 people. They got about 1,100 replies. And again, you don't need to go through all these in detail, except to realize that in the 10 years or so intervening years, and with a larger sample, albeit a self-selected sample, there's still no agreement. People are still wondering what all this quantum theory means. Well, One of the important lessons from this is that it's possible to proceed with an endeavor without having answered all the fundamental questions. And if that's true of quantum theory, so there's no agreed consensus about what happens when you make a measurement of a quantum system. Nevertheless, those of us doing experimental work in quantum carry on doing the experiments because quantum theory is too robust and the arising technologies are too important to halt the endeavor pending deeper understanding without losing a desire for deeper understanding. You can apply that to other areas of life. Right? You can apply it to marriage, you can apply it to bringing up children, you can apply it to the spiritual life. I don't suppose if we were to go around this room we'd find complete consensus about what happens when you pray. Nevertheless, prayer is too important and too robust to stop while they're still trying to think through the answers to that question. Well, the quantum technologies forge ahead, and I had a good discussion yesterday with one of the board members here at IIT, and we're hoping that IIT here will develop a quantum technologies program. And my own company, Controlox, offers a suite of software which I think will be really useful in the development of quantum computing courses here at IIT. And indeed, the software is suitable for students to use and for teachers to use if they're teaching a course. But for those who want to go further into the development of research in quantum computing, there was a big announcement in some of the Indian press about, December the 10th, just over 2 weeks ago, about a new product that Controlox has launched here called BBSR. And BBSR offers a complete quantum computing system, ready-made, but with an open architecture so that it's very suitable for people to experiment on it and explore it. The name comes from a Sanskrit word because it was specifically developed for users here in India. And Vidyakar comes from this Sanskrit word meaning causing wisdom, giving knowledge or science, which we think is a very appropriate name for it. Now, if we're trying to understand how we describe reality, we're trying to make true statements about it, we have to recognize that truth and our statement of truth depends on choices that we make. And that sounds rather scary for someone coming from Oxford. You say to me, well, does that mean you're a postmodernist, Professor Briggs? You think what's true for you is different from what's true for me? No, this is not postmodernism. It's not saying there's no absolute, but it's saying that if there is a reality, and truth is a label for our attempt to describe reality, then what we describe will depend on choices that we make, because it will depend on where we look, it will depend on what evidence we choose to consider, it will depend on the intellectual tools that we choose in order to address and evaluate that evidence. And this came to a head not in a science subject, it could have done, but it came to a head in the study of history in the 19th century. One of the great 19th century pioneers of history was Leopold von Ranke. He was extremely influential. He drew a distinction between Geschichte, which is, as it were, sort of factual history, and Historia, which is more a sort of narrative kind of interpretive history. And he was passionate about seeking to describe Geschichte, wie es eigentlich gewesen. I've given you an English translation underneath. He merely wants to show how it actually was, history as it actually happened. And the word eigentlich in German allows more than one interpretation. It could mean history, as it actually was, or it could mean history as it essentially was. In other words, digging down under the facts to understand the essence of what's there. But either way, seeking to describe history as it actually happened is a hopeless task. Supposing you thought that a good way of doing history was to have a video recording, all right, because a video recording would be completely accurate, it would be completely factual. But you'd still have to decide which direction to point the camera, and what zoom to use, and whose voice to record in the video recording. And the way that's often used of illustrating this is of a map. I'm a pilot, as I've told you. This is an air map over a part of England that is Southend Airport. We often fly through this area when we're flying over to the continent, Diana and I. And this is a fabulous map. It's very, very accurate. I could tell you what every detail on that map means. And I would make use of some of those details when I'm flying. And I need to have all of them available to me. So is this a true map of Essex? Depends what you want to know. If you're trying to find the route to drive to your Aunt Mabel to have Christmas lunch with her, it's not a very useful map. So it's an accurate map for a particular purpose, that is for flying aeroplanes through this area. But it's not a useful map if you're a public utility company and you want to know where the pipes are buried under the road. And this concept of a map actually was also illustrated in the 19th century by an amazing Oxford mathematician and children's writer called Lewis Carroll. Does anyone in India read the Lewis Carroll books, Alice in Wonderland? You read Alice in Wonderland, okay, Alice was a little class. Here's what he said in another place. He said, we actually made a map of the country on a scale of a mile to a mile. It's never been spread out yet. The farmers objected. They said it would cover the whole country and shut out the sunlight. So now we use the country itself as its own map, and I assure you it does nearly as well. So this question of a map, the accuracy of a map, depends on the purpose. And questions of purpose are questions of human choices. We choose the purpose for which we want the truth. In an English court of law, if you're called to give evidence, you have to say something like this: I do solemnly, sincerely, and truly declare and affirm that the evidence that I shall give shall be the truth, the whole truth, and nothing but the truth. Now, I would feel rather nervous if I was asked to make that oath, because I might say, well, if I was questioned, I might say, well, I saw the witness, I saw the accused at 6 o'clock. And if the lawyer was a sort of scientific nerd like me, he would say, well, what uncertainty? What are your error bars in this statement? And there's a whole lot that you've not told us. Where was he? What was he? How was he walking? What was he wearing? What was his facial expression? And I don't know how you give a true statement of someone's facial expression anyway. Right? So if I was in a court of law, I'd want to sort of qualify it and say, well, insofar as it's relevant to the case in hand, and insofar as it's sufficiently accurate and reliable to inform and not mislead the court for the purposes of the decision which the jury is required to reach. And these are rather strong qualifications of the statement. So, if truth depends on where we look, and the tools that we're going to use, the intellectual tools for teasing out the truth, how are we going to address the truth about God? That there have been people, there are still some people, who say, well, once you've got science, there's no room for God, there's no place for God. You explained everything by science. In my view, that's a very impoverished account of human flourishing. And I'm not alone. There are plenty of accounts out on the bookstall, actually, of people who've been involved with the spirituality centre here, including quite a number of Nobel laureates. Here's someone who was not a Nobel laureate, but he was a Templeton laureate, and he happened to be someone who was a great mentor to me. John Polkinghamore. He says the poverty of an objectivist account is made only too clear when we consider the mystery of music. From a scientific point of view, it's nothing but vibrations in the air and the eardrums and stimulated neural colour. How comes they come about that this banal sequence has the power to speak to our hearts in eternal beauty? The whole range of subjective experience, from perceiving a patch of pink to being enthralled by Bach's Mass in B minor, onto the mystic's encounter with the ineffable reality of the One. These are not to be dismissed as epiphenomenal froth on the surface of the universe, whose true nature is impersonal and lifeless. A few weeks ago, a very distinguished Oxford professor, John Carey, died. John Carey was professor of English, actually, and he wrote a wonderful, or he compiled a wonderful book, The Fable of the Science, which was some of the science writings that he thought were really fine pieces of English writing. In the preface, he said this: science cannot be regarded as inherently anti-religious. On the contrary, its aims seem identical with those of theology, in that both seek to discover the truth. Science seeks the truth about the physical universe, theology about God, but these are not opposed objectives. Well, theologians, or at any rate Christian theologians, believe that God created the universe and so may be contacted through it. Actually, it's quite funny because he goes on in that passage to say what he thinks is the antithesis of science. Can anyone guess what that might be? What do people think is the antithesis of science? Anyone want to guess what John Carey says? Nobody's brave enough to try. He actually said, is it actually the antithesis of science? It's politics. He went on and described why he thought that. And it's because of the way that science and religion are both passionately concerned with the truth. That the artist, a friend of mine who's an artist from America, and I wrote The Penultimate Curiosity. And the penultimate curiosity is an account of the way how, throughout history, where you've had a culture or community, or occasionally it could be an individual, who cares about the big questions of truth and purpose and meaning. Why are we here? What are humans for? What is God like? How can God be known? A concern for those questions has time and again proved conducive to the sort of curiosity about the material world that eventually became the sort of science that I do in my laboratory. We made a film, while the book was in production at Oxford University Press, we made a film which is available on the web. I can give anybody who wants it a link to stream the film, but I'll just show you a little sort of trailer for the film now. So this is Roger Wagner and me flying around the Mediterranean in pursuit of the penultimate curiosity.
In the book that Andrew and I wrote together, we traced these motivations as far back through history as we could go. And now we're going on a journey to explore some of the key places in the long and extraordinary story that we discovered. I can remember that in the 1990s, what people called the human revolution only happened when Homo sapiens migrated from Africa to Europe and started making paintings.
And what changed that was the discovery in the Blombos caves in South Africa of evidence that people were making symbolic markings 100,000 years ago.
I mean, in the newspapers they described it as the first artist studio, which I love, because they found these extraordinary abalone shells which were used for storing and actually mixing pigment.
Only last year in Indonesia they discovered evidence that when humans started to migrate from South Africa, one of the things they took with them was painting.
And the first European paintings were discovered just about the time we started writing this book.
Or at least thinking about it, yes.
Yeah, and that's where we're going now.
A las Vegas!
This journey will take us across the world and across time. It will begin in France with that discovery of a vast complex of prehistoric paintings. Paintings that the leader of the excavations is convinced were religiously motivated.
We know they have a religious motivation, first because people didn't live inside those caves.
But paintings which also show an astonishing attention to anatomical accuracy.
Doing it with such accuracy might have been vital because they were recreating them.
It was made perhaps 35,000 years ago, and it's an astonishing piece of work. The journey will take us on to a city on the coast of eastern Turkey.
I mean, the ruins are somewhere inland, so I'm not sure we'll see them. This is 200 BC. The letters from the coastal town, a wonderful centre for new thinking.
A city where, in the 6th century BC, a new idea of the divine coincided with a new kind of interest in the natural world. From there we'll follow the route by which one man brought this idea to 5th century Athens.
Partha said he was the first person to work out how the shadowing of the moon was related to the sun. Yeah, and he also said that the sun was not a god, but a fiery ball, which in 4th century Athens must have been a pretty controversial thing to say. Yeah, I think he was probably quite a courageous chap, actually.
And visit the places where it provoked opposition and sparked a whole new way of thinking about the gods and studying the world. We will follow the path of these ideas to Alexandria in Egypt.
Well, what happened in this great multicultural city when the philosophical religion of the Greeks and the revealed religion of the Jews and Christians came into contact? Well, the answer was riots.
But we will also see how in a newly discovered philosophical school, where Christians and pagans studied together, a Christian philosopher who insisted that nothing should get in the way of truth, anticipated one of Galileo's most famous observational experiments by almost exactly 1,000 years.
Two unequal weights dropped from a given height strike the ground at almost the same time.
Following this trail forward to the city of Pisa in the 16th century, we will discover how Galileo not only repeated that observation, but followed in that early Christian philosopher's footsteps in his conviction that pursuing truth as a Christian duty would reveal deep laws that govern the whole creation. Coming back to Oxford, we'll see how in the 17th century religiously motivated natural philosophers sparked what we now call the scientific revolution. And finally, travelling first to Scotland and then to Cambridge, we will see how a 19th century scientist wrote down 4 equations which showed that the whole universe was filled with the surge of electromagnetic waves.
Their description of the fundamental gearing between space and time led directly to Einstein's theories, but they also provide the basis for all the electronic technologies that shape the modern world. The world we live in today begins with these equations.
And we will see how for that 19th century scientist, the discovery of those 4 equations, which revealed the deep unity of fundamental aspects of the universe, was carried along.
Human beings seem to reach out beyond the horizon of the visible world in order to try and make sense of it as a whole. You could describe it as ultimate curiosity. If then our curiosity about the world around us moves, as it were, in the slipstream of that ultimate curiosity, you could describe it as penultimate curiosity.
Well, some of you may care to read the book of the Penultimate Curiosity. For me, this is a continuing journey, and so with 2 other friends, I explored it further, and we wrote a book which we called it Keep On Seeking, which explores these things further. if we're going to tackle the big questions that face us, we need transdisciplinary engagement between knowledge systems. So we need science, which is based on observation and theory and experiment. And we need the knowledge system of religion, which is based on scripture and tradition and reason. And transdisciplinarity involves the participation, bringing these together with partners outside academia, and a great openness to other sources of knowledge, different perceptions of the problem, and different value commitments. So you can think, what is science? Well, science is a socially organized and institutionalized form of praxis where publicly available knowledge claims are scrutinized by peers and critically tested against empirical phenomena. So what is faith? Well, faith is the assurance of things hoped for and the conviction of things not seen on the basis of evidence and extending beyond it, usually done in communities of faith that offer scrutiny and support. So science is derived from a multiplicity of methods and aims to provide a basis for understanding our world. And faith arises also from a multiplicity of sources and aims to provide the basis for knowing God. And we say quite a lot more about that in the penultimate curiosity. So what are the hallmarks of science? Well, justified knowledge claims, explanations based on the phenomena, vetted through peer review, and driven by curiosity and utility. You can match that with similar but distinct statements about faith. It's warranted belief claims, its belief is close to empirical data, it's refined through scholarly tradition, and it's driven by a desire to know and serve God. And so, you can look at these various attributes that you look for in each. Truth fit for purpose. Uncertainty is a mark of integrity. Perspectivity, in other words, recognizing the importance of different perspectives. Youth aspires to universality, and necessarily in both areas there is the social reality of power that needs to be taken into account. So what are the societal guardrails that we have for human flourishing? Well, one of the big changes that's taking place in economics at the moment is a shift away from describing, well, for the purpose of economic modeling, they had this picture of Homo economicus, a man who was rational, selfish, greedy, and lazy, seeking to get the maximum utility at the minimum cost. And it's not that humans never behave like that, but if you think that's the only thing that motivates you, you're missing out on something pretty substantial. So I'm trying to replace it with Homo fidelis. Sometimes humans behave as ethical, altruistic, generous, and energetic. Another important rule is in the purpose of corporations. So what is the purpose of a corporation? Corporations are the engines of our economies. Well, they're to provide solutions for society, and they can be profitable solutions. They've got to be profitable, otherwise the corporation won't survive. But without providing problems for society. And this requires a transition from companies maximizing shareholder value to companies promoting human flourishing. And what I mean by that is summarized in the book on human flourishing. Now let me rather quickly give you a worked example of this in the field of AI. So in the field of AI, we've had this extraordinary phenomenon in the last 3 years with the rise of the availability and use of generalized pre-trained transformers for large language models. One of the dangers is that they work by harvesting all the available information on the internet. A growing proportion of that information on the internet is itself generated by large language models. This is a picture from a medieval bestiary in one of the Oxford libraries. in the medieval times, people would, there was no printing, and so people would, monks usually, would copy previous pictures of animals. And often they were extremely beautiful pictures. Here's one, here's another one, here's a third one. The trouble was, they were making copies of copies of copies of copies, and the animals depicted grew more and more unrecognizable to us who actually look at the animals. One of my great heroes in the 13th century in Oxford was Robert Grosecrest, who encouraged people to go out into the woods, the forests around Oxford, and actually look at the animals for themselves and see what the animals looked like. And so there's a danger that increasingly the LLMs will be like the medieval bestiaries in detached from realities. There are people addressing that problem. A bigger problem is the harm that these large language models are doing to people's psychology and mental health, and the most vulnerable are the adolescents and young people whose brains are in the process of transforming into adult brains. In the UK, we grieve that the death of this lovely 14-year-old girl, Molly Russell, who took her own life, almost certainly under the influence of LLMs. There's now a growing number of families actually who are suing the big companies. This is Adam Rain, took his life earlier this year, also 14 years old, because of, the strong influence of the machine learning feeding him information about how to take their own life. There's another lawsuit that's going on as we speak. It was announced a couple of weeks ago, where in this case it's because of teenagers who've taken their own lives as victims of what do you call it, sex bots. You know, that they're being blackmailed by the system because of pictures they've had of themselves. And we've got to address what these AI instruments are doing to us. Here's Jeff Hinton, who in 2024 shared the Nobel Prize for his work on machine learning. A year ago, he resigned from Google so that he could speak out. The idea that this stuff could actually get smarter than people, I thought it was way off. I no longer think that. And in the summer this year, he was interviewed in the Financial Times, and he's worried now about a different problem, which is the capacity of AI to increase the gap between the haves and the have-nots. That people like me who, develop and use AI, and the people who don't, and whose jobs may be changed or displaced by AI. Here's Tim Berners-Lee, the inventor of the World Wide Web, who's got a book that's just come out called This Is For Everyone. He says these systems are designed to be addictive, feeding more and more extreme content, making them alternately angry and sad. The new age of machine intelligence is arriving, and the immense power of such systems will be as good or as evil as we permit. Every AI system has values built into it. When we were developing it for our work on quantum devices, we spent almost as much time. Is all well? Is that telling me to stop? Okay. We were developing the algorithms, but we spent almost as much time developing the score function. What did we want the algorithms to optimize? And as a society, we're going to have to examine where we want the values to come from that are going to be incorporated into our AI. Where do values come from? One possibility is that they just come from human rational thought. We think up what we like the values to be, and we seek to persuade others to adopt our values. But there's another possibility, and one which I myself embrace, which is that there is a moral reality that is just as real as the material reality that I seek to study as a scientist. And people adduce quite a lot of evidence for this. Nigel Bigger, Oxford professor of ethics, says he's been struck that when he goes to different cultures, he finds that they have an ethical basis that seems to have no historical root to the Christian ethical basis that he pursues. Francis Collins, very distinguished, well, he was the director of the Human Genome Project and subsequently the director of the National Institutes of Health in America. One of the key factors in his coming to a Christian faith was the recognition of moral realism. This seemed to him to be so significant that it made him seek God and eventually find God through Jesus Christ. You can think of the golden rule: whatever you wish that others would do to you, do also to them, for this is the law and the prophets. And something like that can be found in almost every religious tradition in the world. So if there's a moral realism, then there's a moral reality that there are values that we can seek to discover. It's easier than discovering the physical accounts of the world, the material accounts. It's going to need different tools. But hey, you know, it's taken us 300 years and then some to get to where we are in science now. We've got to be prepared for a comparable endeavour if we're going to explore this moral realism. As we face new challenges, like the challenges of AI, we may also need to be creative about values. And you can think of a sort of analogy between the relationship between engineering and physics. Okay? Engineering is a creative activity. You're making new things, but you've got to make them in accordance with the, with the scientific basis that has been teased out so painfully and so carefully over the centuries. So if we're going to do this value creativity, it's going to have to be, rather as engineering is to physics, it's got to be related to the moral reality that I believe we can discover. And you can think of various opportunities that there are for that, particularly in the context of AI, but not only in the context of AI. So, why does human flourishing need both scientific insight and spiritual wisdom? Well, the nature of humanity includes responsibility in a world that's increasingly shaped by science and technology. And you can think of machine learning, you can think of quantum computing, you can think of biomedical technologies. Accountability is part of life, philosophically, ethically, and religiously. And if accountability follows responsibility, then rather quickly you find yourself asking, well, accountable to whom? And if we're asking accountable to whom, then what are the values against which we're going to be held to account? And then we've got to discover where those values come from. Thank you very much.
We would like any questions?
Thank you, Professor Briggs. It was very, very interesting presentation. I will slightly try to translate this into a contemporary philosophical language. So you started with the idea of the primacy of doubt. And of course you traveled to human flourishing, ethics, rationality, science. It was a wonderful journey. Actually, in contemporary critical theory, they say that there is a series of crises. Legitimation crisis, system crisis, knowledge crisis. You are also, you were actually in your presentation hinting at all these. So in all these crises, the problem is the primacy of the doubt. about legitimization of social systems, knowledge, education, environmental crisis, all that is coming there. I'll just share a personal experience.
You will allow time for others to ask questions.
No, just 1 second.
Yes.
Just 1 second. I used to write in Indian Express. So I sent a paper about the porous border between cosmogony and cosmology. They are published. And where I was telling the argument of Lawrence Krauss, this cosmologist, who was flatly denying any kind of dialogue between cosmology and cosmogony. Cosmogony is basically a kind of mythical worldview. There also we have dark matter, dark energy and all that expressed. And very politely the editorial team replied it to me saying that this will create some kind of superstition.
Will you allow time for others to ask questions too?
Yeah, sure. So since it was very interesting, of course we are going to talk, there's no problem. So would you like to comment on this? The nature of dialogue that science and humanity should make.
Yeah.
Keeping the primacy of doubt in mind and human flourishing. Thank you.
I think David Bacon has thoroughly demolished Lawrence Krauss's position, and I'm afraid he had to leave Arizona State University for other reasons too.
That I do not know.
I'm going to move on to the next question.
I think please be give pointed questions so that Professor Briggs can give a pointed answer. Any questions, please? And please try to be brief.
Hello. Yes, sir. It's a very wonderful talk. So my question is like when we talk about quantum information, we take the basis as like unitary and linearity, right? So in contrast to classical information which get lost, but in your experiment you showed that quantum information is erasing. So please comment on this, please.
So what is your question?
Like I want to ask that in quantum information are never lost, they remain conserved. But in your experiment, which you are saying that it is erasing.
Yes.
Can we recover it?
Yeah. So what you needed to do is, I'm so sorry. And this was specifically quantum mutual information, all right, which goes beyond quantum information. You can have mutual information in a classical system. And one of the discoveries of the last 10 years or so is that mutual information can be a driving force. So, for example, if I've got a hot object here and a cold object there, and I connect them, you would normally say, if you know your second law of thermodynamics, that the hot one must get cooler and the cool one must get hotter, unless they share mutual information. And mutual information can actually be consumed and drive it the other way, so the hot one gets hotter and the cold one gets colder. Now that can happen with classical information. And in this experiment we were doing it with quantum information. And the crucial step was to take this linear Bose-Einstein condensate and segment it, all right, and say that we're going to consume the mutual information between this segment and that segment. And in this case, the mutual information arises from quantum entanglement. It was consumed in the experiment. Now, I know where your question is coming from. If that's a closed quantum system, how can it happen? There's some very detailed mathematical analysis of it, which I won't go into now, but it's been published in Nature Physics. But basically, it's saying that it's a Klein-Goldstein Hamiltonian, all right, does allow the quantum mutual information to be consumed and dissipated in that experiment. And it just illustrates how counterintuitive quantum physics is. It just isn't like anything that we're used to, and it just is different. And what an amazing discovery journey it's been for 100 years or more to explore that and its implications. So I share your amazement, but you know, the experiment's been done and it works.
Thank you, sir.
We can go for one more question.
Good morning, sir. I'm very humbled to have this kind of conversation, touching upon various aspects of knowledge, science, theology, and philosophy. My point of question is that what is the converging point between science, philosophy, and theology? Why science is in denial of what philosophy or theology is claiming? I do know that the science is at current juncture is facing with lot of puzzles like observer effect and superposition of the particle. Why they are kind of in denial of accepting, or you can say objectively rejecting the philosophical claim or theological claim?
I think that the short answer to your question is any attempt of science to deny the theological frame is doomed to failure, because it's a different kind of knowledge system. It's a different kind of intellectual endeavor. If it had been successful, then you would not have all the books and the posters that you've got out there in the hall of very distinguished scientists of strong faith. And the ones that I know best are the ones of strong Christian faith. Denial of philosophy, well, that's a bit different, because the relationship between philosophy and science is a bit more subtle. But basically, philosophy is a discipline of intellectual tools. Philosophy provides us with the intellectual wherewithal to tackle other big questions. Now, just occasionally, it is possible to test philosophical theories in the laboratory. I've done one myself. It was a test of macrorealism, which was an interpretation of quantum theory that had been devised by Tony Leggett in the 1980s with his student Anupam Garg. And we were actually able to do an experiment that violated the Leggett-Garg inequality and therefore ruled out a very technically defined macroscopic realism in the experiments that we did. So just occasionally the science can shed light on the philosophy in a way that we did. So that was very exciting. It was a very exciting experiment to do. But usually philosophy is providing us with thinking tools. That's what it usually does. And so probably we're more likely to use those thinking tools in our science than to refute them. All right? But when it comes to the relationship between science and theology, I think theology needs to be informed by science, and it's a matter of historical fact that science has been informed by theology over the ages. That's what we wrote about in the penultimate curiosity. And so basically the relationships between these three should be ones of harmony. And that is usually the case. There have been a few historical upsets which have been well documented. You look very puzzled. You disagree.
Can we conclude that science is kind of fearful to go beyond cause and effect?
You'll have to speak up.
Probably, Professor Briggs, if I might interject,
yes.
Because I am getting signals that we are running out of time.
Oh yes, we should stop.
So, what I understood from Professor Briggs is that truth is relative. So, as a scientist, you can prove what you want to prove. If I might, take your word for that. And once again, I will thank Professor Briggs very much for his informative talk. And we do expect that, what he was trying to discuss, at some point it will get a more concrete shape, and we will listen more from you in the future. Thank you. Thank you, sir.
Professor Briggs, for that enlightening start to the day, challenging how we perceive the fabric of reality. Your lecture and especially that short video made all of us really ponder on the perception of our reality. Also, a very big thank you to Dr. Ray for chairing this session.